Hi, I'm Henry. Today I'm going to talk about using counter machines to find cliques and cycles. In reality, I'm only going to talk about cycles. I don't have loads of time, so I'll do what I can. I should probably mention this is part of a joint work with Marvin, Philip, Leah, and Carol that's under review at the moment. So seems that it's probably correct, but I'll put an asterisk on that for now. But yeah, I'm excited to share this problem with you. I'm just going to dive straight in. So first, I'm going to show an easy problem. I'm going to kind of scale it up to the problem that I study. So first, path in a directed graph. If I ask you from E, can you reach G in this directed graph, then the answer is yes, right? You can just run BFS or DFS and it works in linear time. I suppose I should probably have put DFS instead of BFS, because if you sort of decided alphabetically, you would kind of go from E to A to B to C to G. Fine, nothing special. I want to make the problem a bit harder, a bit more interesting. So I'm going to add small weights to the edges. I'm going to label them with -1, 0, or +1. And I'm asking about a slightly different problem now. I'm asking for this, quote, never negative path problem. So I'm now asking from E, can you reach G where every prefix of the path remains non-negative? So you can think of this as when you're at E and you add the weights at the edges as you step along, that the value that you maintain stays non-negative. So the path we saw previously is not okay anymore, right? So if I go from E to A, I immediately take a negative prefix, which is not allowed. So I have to do something a little bit more intelligent, right? Like I can see E to D to G, right? I get +1, and I'm safe. Still not particularly difficult. You can probably modify your favorite shortest path algorithm to do something here. Shortest sounds strange, right? Because that would probably imply that you do want to take negative weights, but if you flip the weights and just maintain and sort of just check every time you take a step whether you're going to take a negative value or not, or whether you're going to take a positive value after you've flipped, then it's okay. And only recently have near linear time algorithms for shortest path come about when you have small weights on edges. So this is kind of maybe slightly more difficult than finding a path in a directed graph without weights, but it's not like ridiculously more difficult. And yeah, like I said, you can go from E to D to G. So I want to make it more difficult. Oh, first, I should probably put it in the setting that I care about. So I call these things one VAS, one for the number of labels on an edge. We're going to update that in a moment. And coverability is really just asking about whether I can maintain this counter value. I sort of imagine it as a counter where I start at E with value 0 and I update this counter as I step along. So that's in the sort of counter machines language, but I sort of try to sell it to you as more of a graph path problem, as a sort of friendlier introduction. So like I said, I'm going to make it more difficult. I'm going to increment to 2 VAS, have to squidge edges around and fill these labels on. Now over it's got 2 labels. They're both small. So the values are like vectors where each component can take value -1, 0, or +1. And I'm going to ask the same question, but component-wise, I need to remain non-negative as I go along. It's already a lot more tricky, right? If I take the path E and then up to A and I fail on the first component, if I go E to D and then D to G, I fail on the second component because I go from 0 down to -1. It's already a bit more tricky. I'm just reminding that both components must remain non-negative. It's not so straightforward anymore, right? Like it's not obvious. You probably spotted though that you can go from E down to D, then you kind of loop at F. This allows you to kind of buy counter value on the second component, and then you can traverse whatever you like. It doesn't really matter. I could have had like a really horrible, expensive path from F to G on the second component, and it would have been fine. But it's not so clear, right? Because I might have cycles that add to one counter and take from another, and I can sort of do some funky trading, and it gets kind of difficult. A little background. So these problems seemingly aren't very difficult in terms of space complexity. So coverability, when you have one component, can be decided in non-deterministic log space. It's been known for a long time. And then soon after that, it was found out that you can update, you can have any number of components, and it's still decidable in log space. So if you care about sort of polynomial running time from like a complexity perspective, we're done, right? Like NL is within P, so who cares? And this is complete for log space, right? Because I know that finding a path in a directed graph requires non-deterministic log space, or at least it's non-deterministic log space hard. There's the typo. This is folklore, and so this is non-deterministic log space complete for any number, right? If I say like, oh, I want 5 components, this is non-deterministic log space complete. So you can solve the problem at a time. But like how much time exactly? I want to know a bit more detail. I want to know exactly how hard this is. And that's what I'm going to talk about today. So I claim that when you have two components, this requires quadratic time. As an asterisk there, that's important. I'm going to do this by reducing from finding a k-cycle in a graph, which is why I've been talking about finding k-cycles. And the observation, if you believe this already, is that this is kind of strictly harder than finding a path in a directed graph, right? I can do that in linear time, and up to the k-cycle hypothesis, this requires quadratic time. So let's see how this goes. So first, probably best to introduce k-cycle hypothesis. This is a very loose way of phrasing it. It's not like an official statement, but never mind. Finding a k-cycle in a graph with m edges requires something like a constant times n squared time. And it turns out that it's fine to do this only for k-circle layered graphs. What on earth is a k-circle layered graph? So you've got k vertex subsets. I've arranged them in a circle pattern, as one would expect. And edges point from one set to the next, like so. So you go from vertex set I to I+1, and you loop back round, and then vertex set k points to vertex set 1. And so they argue that finding a k-cycle in a graph like this with m edges requires something like m squared time, which is surprising, but it kind of gives you a sort of very fine hardness in a sense of finding a long cycle in one of these. So how on earth am I going to construct an instance where I've got weights on edges in these kind of two VASs, and I'm going to ask for a coverability instance? So firstly, I'm going to kind of like break apart this circle graph. I'm going to take a copy of V1 and a second copy of V1. I'm going to put them on extremes, and I'm going to like run edges from left to right. So this is now no longer a circle layered graph. This is kind of like a sort of drawn out version of it. And you can kind of imagine that if there was a cycle in the original graph, then I kind of want to pick a node in V1 and a node in V1 prime that match, say, maybe the bottom nodes. And if I can find a path through here, then I'm done, right? Like that would correspond to a cycle in the original graph. How on earth do I know that I start and end in V1 and V1 prime at the same point? I'm going to use my counters or my weights to enforce this. So I'm effectively going to use two components, and I'm going to load an ID number of the node that I select onto them. So the first thing I do is I start at S and I just load a load of value up. So I get like, I don't know, to 10 on each component. And then on the first component, I select the ID and I add that on. On the second component, I take it away. So maybe I've got to like 10 and 10. Maybe I choose the top node, so I'd add on 2 to the first and I'd take away 2 from the second. And I do the opposite on the other side. So I run through, I then subtract the ID from the first and add it to the second, and then I take away 10 and 10 from the other two. Note that the amount I need to update each component needs to be something like the size of V1. It's like linear in the number of nodes, so it's not a particularly large thing. And I claim that you can get from S, and you can cover over to T, if and only if there's a k-cycle. The idea is that suppose you leave via the ith node in the first V1 part, and you arrive via the jth node in V1 prime, then, well, the first component ensures that the ith selection was at least the jth selection. So, and the vice versa for the second component. I guess it's probably better to think about the example. Imagine you started from the red at the bottom and you arrived up here at the top in the blue. Just pretend. I know it's not possible, but just pretend. Then you would have only updated the first counter with, say, 1 on the left, and then you decrement it 3 or 4 times. You then have this mismatch, right? Like you end up overall net subtracting from the first counter. So you have about 8 value when you're here. And then when you fall down this path, you would kind of die at some point, right? When you get near to T, you would have subtracted 9 from 8, and now you're negative, and you wouldn't have managed to get there. Yes?
All the edges in the middle are 0, 0.
Oh, yes, that's a very good point. I forgot to say. If an edge is not labeled, it's not touching. It's not touching a weight. Yeah, that's very important. Thank you. And so the first component ensures that effectively that the red circle is at least as high up in node ID as the blue, and vice versa for the second component. And so the two together, which is why I have 2 sets of weights, give you equality. They say you leave V1 and arrive at V1 prime, so the start and the end are the same. So if I was to then like wrap it back into the circle-layered graph, I know that there is a cycle starting and ending at that node in V1 originally. And so what you can conclude from this immediately is, if you sort of believe the hypothesis of finding a cycle, a k-cycle in a graph of m edges requires something like m squared time, I gave you a linear time reduction. It's linear time because when I copied the graph, I copied V1 twice, it's still linear. And I kind of had this prefix and suffix, which were roughly the size of V1, that's all linear. And the number of edges in this graph bounds the number of, like, in the original graph, bounds the number of nodes and edges in the entire 2 VAS that I showed you. And so if this thing has size n, which is like the number of nodes plus the number of weighted edges, then this requires quadratic time as well. So if you believe the hypothesis, then this is fine. And that's it. Thank you very much. I just wanted to share a nice idea with you. Hopefully there's time for questions.